This chapter talks about the Bernoulli equations. So before this, we already discussed the mechanical equations, the energy equations. Now we go into the Bernoulli equations. Basically, all of these equations, they are almost similar. Only the terms, how they define the terms, is different. If you look at all of these equations, they are very similar, and you just have to memorize only one of them. And by changing the way how they express the terms, you can change from one equation to another. Some explanation on the Bernoulli equations. It approximates the relations between the pressure, velocity, and elevations. It is only valid in steady regions, where you can see from the figure all the streamlines that are all steady regions. Meanwhile, behind the airfoil that we can see here, these shaded regions, it is unsteady regions where it's a wake emerges from the back, from the airfoil itself. So these regions is where Bernoulli equations is not valid, okay, due to the unsteadiness of the fluid in that regions. It is also only valid for incompressible flow and where frictional forces are negligible. And this Bernoulli equation is very useful in showing the relationship between those variables mentioned, okay, between the pressure, velocity, and elevations, how they correlate with each other. What is the effect? Like for example, in the same streamlines, what happens if the pressure decreases? What will happen to the velocity? And what will happen if the elevation is different? So by understanding the Bernoulli equations, you can find the relationship between those terms. And as I mentioned before, Bernoulli equation is very important for those who are taking aerospace, because the main principle behind this how you can fly things relies on the Bernoulli equations. In two-dimensional flow, the accelerations can be decomposed into two components, which is the streamwise components, which are the accelerations that is along the streamlines, and the normal accelerations, which is perpendicular or normal to the streamlines, which is given by A normal equals to the tangential velocity power of 2 divided by the radius of the curvature. The streamwise acceleration is due to the change in speed along the streamlines. However, the normal acceleration is due to the change in the directions. So that means that if the particles in a streamline move in a straight path, an is equal to 0 because the radius of the curvature is infinity. So that means that there is no change in directions. So the Bernoulli equation results from a balance along a streamline. The equation shows here is similar to the one that we've seen in the momentum equations, where the total accelerations is equal to the local accelerations and the advections. So this is what we've seen before in the momentum equations before. This is the accelerations, and this is the local acceleration, which is as a function of time. And this is where it's due to the advections, where the s over dt is velocity, or where we've seen before, it's just quite similar to the one that we've seen at u del u over del x, something like that, and plus v del u over del y. This is quite similar to this. This is elevations. All of these terms you have seen this before, and it's very common. And as you know, that velocity is a rate of change of displacement with respect to time. Okay, the Bernoulli equations derive from the summation of all forces acting on a particle in the fluid. So we have this is like the particle in the fluid, and you have these forces due to the pressure. And as you know, that force is equal to pressure times area. So pressure times the change in area here. So just by total out or summing all of these forces acting on that particle, you can do some derivations. So you don't really have to memorize all of these derivations. Actually, we are more into the how to apply all of these equations. But actually, it's quite a good thing also if you can try to understand how this is derived, so that you can appreciate these equations. Okay, so this is the summation of all forces, and this is the rate of change of momentum. And just by substituting that mass equals to the rho v and etc. w, you have this the vertical component of forces acting on the particle. By substituting, you will get the Bernoulli equations. Bernoulli equation is only for incompressible wear. That means that the density is constant. And the Bernoulli equations happens between 2 points on the same streamline. So we take this line, for example, as a streamline. So like 1 point to another, the total energy is the same. The energy at point 1 and at point 2, as long as it is on the same, it lies on the same streamlines, the total of this flow, dynamic and kinetic and the elevations or potential, the total of them are the same, it's conserved. These two equations, it shows the Bernoulli equations for general case, where the density for this one, where it's like might have a different density, but usually since that Bernoulli is derived assuming that the flow is incompressible, so we take the density as constant. So basically this is the Bernoulli equations. Okay, the bottom one is the Bernoulli equation where it is incompressible flow, which means that the density is constant. Okay, the Bernoulli equations can also be viewed as the conservation of mechanical energy principle. The difference of this compared to the mechanical energy that we learned earlier is that this does not involve any conversion of mechanical energy and thermal energy. So that means that there is no energy loss, there is no like additional energy supplied into the flow from shaft work, for example, or also from like thermal energy, where the thermal energy is where it dissipates from the flow. So there is nothing like that. So there is no energy loss in Bernoulli equations. And the Bernoulli equation states that during steady and incompressible flow with negligible frictions, the total energy remains unchanged, but the form of energy may be converted to one and another, where it may convert from flow into kinetic or kinetic into the other way around and the other way around from potential energy. So they can just change from one form to another, but the total energy remains unchanged. There is no dissipation of mechanical energy into irreversible energy loss, and this equation is quite commonly used in engineering practice. Okay, as it was mentioned before, Bernoulli equations can only be applied on the particle along a streamline. However, by using the force balance, it can be used across streamlines for steady and incompressible flow. So for flow along a straight line, the radius of curvature is infinity, as is mentioned before. We have like lines and the radius of curvature where it is close to infinity, is reaching infinity. So radius here is infinity. So that means that that part, the velocity part is divided by the curvature, by the radius of curvature will become 0. So what is going to give you will only have this. This is when you have a straight streamlines. Basically, that means that the velocity of the particle in that fluid remains unchanged. So this actually also expresses the variation of hydrostatic pressure with vertical distance for a stationary fluid body. So in A, you can see from this figure where we can see the relationship of the radius of curvature with the pressure at 2 points, point A and point B. So at A, as you can see that it is at the outer curve. So we can expect that the radius of curvature for A is higher. So when the radius of curvature of A is higher, what is going to be at the V squared over R is going to be low. So when it's going to be low, and we take that the elevation of A and B is quite similar. So that means that the pressure at A is higher than B, because the radius of curvature at B, if you look at the equations, the radius of curvature at B is lower. That means that the kinetic energy at B is higher. So since the total energy is remain unchanged in the flow, it will be compensated by the flow energy, which is due to the pressure. So from here we can see that the pressure at B is lower than A, but the kinetic energy at B is higher than A. So that's how we can relate between these energies in the flow by using the buoyancy equations. Okay, this equation is for unsteady and compressible flow, but as we know that Bernoulli equations actually only can be applied for steady and incompressible, so we can just skip this. It's not going to be used, and it's not actually valid also as well. Okay, so this slide shows the difference between 3 types of pressures: statics, dynamics, and stagnation pressures. The first term we see here, actually this is a static pressure which does not incorporate with dynamic effects due to motions. Meanwhile, the second term here is the dynamic pressure, as we know that when it involves velocity or motion, it has this kinetic energy. So here you can see there is a V terms here, velocity. So that means that this is where the motion actually affects. So as we know, when it has effects, it has kinetic energy. Okay, meanwhile, the third term is due to the hydrostatic pressure. It is pressure due to the level of the elevations of the fluid. So the total pressure of this is the summation of these three pressures: static, dynamic, and hydrostatic. Next is definition on stagnation pressure. Stagnation pressure is the sum of statics and dynamics pressure. It is useful in measuring the velocity of a flowing fluid. The example of application that is using this pressure, stagnation pressure, is pipette static probe. So on the probe, there are several holes to capture both static and dynamic pressures. As you can see, the holes, and you have several holes at the side of that tube. So how actually it works, this hole, the first hole here, it will facing opposite to the directions of the flow. So it's going to capture both the dynamic and static pressure of the fluid. Okay, meanwhile, the pressure at the side of the pipette tube will be perpendicular to the flow. So it's not going to capture the pressure due to the motion of the fluid. It will only capture the static pressure. So actually it's quite similar to the first tube here. It is perpendicular where the flow is moving this direction. So it's not going to be affected by the velocity. So this is the pipette tube. This capture the both stagnation, which means that it's capturing both dynamic and static pressure, and this one is capturing static only. So how you want to find the velocity? Just use, basically this is equal to the first one. This is the stagnation pressure, which is the static pressure plus the dynamic pressure. This is the one that is being captured by the one on the right. And then the piezometer here, only captures this P. Another one, the one that is bent, it captures both of them, P plus rho V squared over 2. The static, it's only capture P. So from there, you know what is P, and P stagnation, you know them because P stagnation is the summation of these two terms, and then you can find what is V squared. Then just change it into these terms, you can find the velocity by using stagnation pressure. Okay, there are several precautions need to be looked into when measuring static pressure. So like for example, if there is an obstacle after the tube, so you have, for the first one, we have some obstacles here. So what is going to happen here is this thing is supposed to only capture the static pressure, but due to the obstacle, maybe like flow is moving, it will be deflected. So what will happen is the pressure here is higher than static pressure because it also captures the pressure due to the motions. So the pressure that is being captured here is not only static, but also some of the dynamic pressure as well. So the second one, this is the smooth one. Okay, this is the correct configurations, where it's only capture the static pressure. Okay, meanwhile, the third one is where we have some like obstructions before the tube. So what is going to happen here, there will be like some separations happens here. And as you know that when you have some weight behind it, the pressure here is low. So here we have the atmospheric pressure. So when you have the difference pressure, it is quite big because PATM and the pressure here is very big, the difference, because the pressure at this region is lower than the pressure at this region due to the weight behind the obstructions. So that's why the pressure that is being captured by the third tube here is lower than what it is supposed to be. And there are some limitations when using the Bernoulli's equations. Okay, the first one, it only can be used in steady flow regions. The second one, it works only on frictionless flow. Third is no energy loss or added in the flow due to the shaft work like turbine and pump respectively. Number 4, it must be incompressible. Liquids can be considered as incompressible because of the nature of liquid that is hard to be compressed. Meanwhile, for gas, the Mach number must be lesser than 0.3. If the Mach number is larger than 0.3, it will become incompressible. Number 5, no heat transfer in the flow because heat may cause the presence of natural flow due to the buoyancy effect on a less denser liquid. Number 6, it can only be used along a streamline. Okay, here are all examples of fluid flow where Bernoulli equations cannot be applied. If you can see the first one where you have a sudden expansion. When you have a sudden expansion, it causes the loss in head pressure, which is contradict to the Bernoulli equation where it says that the total pressure in the same streamlines must be equal, but somehow due to the sudden expansion, there will be head loss in that region. So the total energy is not the same anymore because one of the condition for Bernoulli equations to be applied is it should be no energy loss or added into the flow. Okay, the second is where we have a long nanotube. It cannot be used. Bernoulli equation cannot be used in this problem because when we have a very long and very narrow tube, the friction of the fluid in the tube will be very high. So the friction here is not negligible, it's significant. So Bernoulli equations cannot be applied. And here we have a fan, where fan actually has shaft work. It provides more energy or more pressure into the fluid. And when you have a heating, it may cause some natural flow to happen. It is also adding thermal energy into the flow, and it may cause the flow, like if you have gas inside, it may cause the flow to be expanded, so it will become a compressible flow. So the example where we have like sudden obstructions and then you have a wake. So these are all examples where you cannot apply Bernoulli equations. So and the bottom here, it shows that when the flow is irrotational, the Bernoulli equations becomes applicable between any points along the flow because the total pressure is the same everywhere. Like at point 1 and at point 2, the total pressure is remains the same. So for this kind of cases, when you have a straight line and it's irrotational, the total energy at point 1 and the total energy at point 2 are the same, although that they do not lie on the same streamline. So for this kind of case, Bernoulli equations becomes applicable. It's about the hydraulic grade line and energy grade line, HGL and EGL. HGL is represent the sum of static and elevation head. So we have static and elevations, which is the first term and the third term. Okay, meanwhile, EGL represents the total heat. So the difference between this and Bernoulli and energy equation and mechanical energy equations, this equation is basically the same, but the way how it's represented is in the unit of height. Okay, if you have basically it give you unit meter. It will give you unit meter. So everything is the same, but the way how it's presented is different. Okay, and Z here, so V squared over 2G here is the velocity head. It represents the elevation needed for the fluid to reach the velocity V during frictionless free fall. Meanwhile, the Z is the elevation head. It represents the potential energy of the fluid. So as mentioned, that this is an alternative form of Bernoulli equation, and it is expressed in terms of head, in terms of in unit of length. Okay, this HGL here represents the static and elevations terms, static and elevations, where energy grade line is the total energy, which is the static, the dynamic, and elevations terms all together. And the dynamic head is the difference between the heights of EGL and HGL. So when you subtract between the energy and energy, basically you will eliminate the static, and you will eliminate the elevations, and you will get the V squared over 2G. So the difference between these two HGL grade line will give you the dynamic head. So below here is an example where if you have the solid lines at the top here, that is the EGL. So EGL is total. It's the static plus the dynamic plus the potential or elevation heads. Okay, meanwhile, the bottom there is the hydraulic grade lines, is static and the elevation. So the difference between these two lines, the gap, it gives you the dynamic head. So in or like this is useful for you if you want to find the velocity of the fluid in the pipe or channel, for example. Okay, so you can see here from the left, you can see that there is a venturi where we have a wide opening to a narrow opening, and then it's diffused into a wider opening. So when it's from here to here, excuse me, you have a wide opening to small opening, you can expect the velocity increase. So at here, the velocity, the dynamic head is zeros because, as you know, that the velocity here is insignificant. Is can be considered or neglected, considered equal to zeros, and then it's increased. So this is the narrow part where the velocity is high, the gap is very big, and the diameter of here and the second tube here is the same. The dimension, the opening is the same, so you can see that the gap is the same. It remains unchanged because the velocity is remains unchanged. But due to that, this is a non-ideal phenomena where there's a energy loss happens here. So that's why the EGL here is not constant. So they will be like, if it's ideal, it will be constant. So actually the difference here, it is the energy loss or head loss due to the frictions in the channel or in the pipe. So then from the second tube to the third tube, we have diffuser. So it has from the smaller gap into a wider gap. So what is going to happen? The velocity is reduced. So when the velocity is reduced, you can see that that's why we have the dynamic pressure is getting smaller compared to the one before the diffuser. That is because the velocity is reduced. And then from the third to fourth to fifth tube, we can see that the gap, the dynamic head is remain unchanged. It is because the opening is constant afterwards. So the velocity is constant, but due to the energy loss, it's reducing, but still the dynamics remains unchanged. So this is how you want to use HGL and EGL to determine the velocity of the flow in the pipe. Okay, there are some notes on HGL and EGL. Actually, if you have time, you can try to read this, where it said that for stationary bodies such as reservoir or lakes, the EGL and HGL coincide with the free surface of the liquid. It is because the velocity is negligible. So as you know that the difference between EGL and HGL is the dynamic head, where in this kind of case, it is stationary. So there is no velocity. So when there is no velocity, EGL is basically equals to HGL, which is equals to the static head plus the elevation head. So there is no dynamic. Okay, for the second one, the EGL is always a distance v squared over 2g above the HGL. Okay, this as is already mentioned before that the EGL is the total energy and the HGL is the total energy but without the dynamic head. It's not without the dynamic head. Okay, in an idealized Bernoulli type flow, EGL is horizontal. Okay, where in idealized Bernoulli type flow, we neglect energy loss or head loss due to the frictions in the pipe. Okay, for open channel flow, the HGL coincides with the free surface of the liquid and the EGL is distance v squared over 2g above the free surface. Okay, at the pipe exit, the pressure head is zeros, where it's because it's a gauge pressure, it's atmospheric pressure. And that's why HGL is coincide with the pipe outlet. And then the mechanical energy loss due to the frictional effects, conversion to thermal, causes the EGL and HGL to like have a sudden decrease downward because there is energy loss. So same goes when you have some like energy added, you have some slope. It's going to increase because of the additional head being provided into the flow. So yeah, it's basically the same here. A steep jump drop occurs in EGL and HGL whenever mechanical energy is added or removed to or from the fluid due to the presence of pump or turbine. And the gauge pressure of a fluid is zero at locations where the HGL intersects the fluid. The pressure in a flow section that lies above the HGL is negative, which means that it is vacuum, and the pressure in the section that lies below the HGL is positive. Okay, this is actually the visual of the ones that's mentioned before, where the first one we see that is the idealized Bernoulli type flow, where EGL's the total heats remains unchanged because there is no loss in energy, in pressure, and in heat. Okay, here is horizontal, and this on the one on the right, there is a jump here due to the sudden heat or pressure or energy added into the flow by the pump. And then you can see that there's a sudden drop here. It is because the energy in the flow, in the fluid flow, is being extracted and to do shaft work. So that's why we have this sudden increase, because the pump provides energy and turbine it extracts energy from the fluid. Okay, and here we have the gauge pressure, which is 0, where the HGL intersects with the fluid, and meaning that the static pressure gauge here is 0, which is similar to the PATM. And then all the pressure at above the HGL will give you negative pressure. That means that it is vacuum. And this technique actually also known as a siphoning, where you use to transfer fluid from one place to another, such as from we want to take out water from pool, or you want to transfer petrol from a car tank to another tank. Use this siphoning techniques. So this is the vacuum. It will suck or it will pull all the fluid here, and then it's moved to the exit. Okay, this example shows water discharge from a large tank. Okay, so it shows the point at point 1 and at point 2, where both of them are exposed to atmosphere. So that means that P1 is equals to P2 equals to the atmospheric pressure. So because they are the same, you can just cancel them out, because when you move them, they will minus each other, and since the value is the same, they can just be cancelled out. So velocity at point 1 is negligible because the area is big. Meanwhile, at point 2, the velocity is noticeable, so you cannot just simply cancel V2. So this is equal to 0, and this will remains there. And then you just need to find the difference between Z1 and Z2. So you can just pick any of these two as the reference. So usually we take the lower one as the reference, equal to 0. Oh, sorry, this is the lower one is 2. So we take that as 0, so we have Z1. But you can also put Z1 equals to 0. So what you're going to get is Z2, you get negative value. Okay, the second example is there is a boy spraying water into air, where point 1 is where the boy restricts the flow. So due to the restrictions from the finger, the velocity here actually is very low because it's being obstructed by the finger. So the velocity here, you can just take it as equal to 0. And due to this obstruction, the pressure is high. Okay. So because it's like when you look at that stagnation point, where we see a lot of this contour before, when you have an object that is obstructing the flow. When the flow is hitting that object, the pressure at that location is high. So P1, you cannot just neglect it. Meanwhile, for Z1, because it is spraying upward, so Z1 will be the lower level. So you can just use Z1 equal to 0. Meanwhile, at point 2, P2 is exposed to atmosphere. So P2, we can just substitute with PATM, and this is the maximum locations where then the water is going down. So that means that this is where the velocity is becomes 0, and then you can find Z2. So from this, if we know what is P1 and we know what is atmospheric pressure, you can find how far the water can travel vertically upward. Or if we know what is Z2, we can find what is the pressure at the exit of the hose. Okay, for this is the one that I told about the HGL, where when this is when the fluid is below the HGL, it will create this vacuum. This is what we call as a siphoning technique of gasoline from a fuel tank into a gas can. So here we have like 3 points. Okay, firstly, the top one, it discuss the difference between point 1 and point 2, which is at the on the surface of the petrol at the gas in the gas tank and at the exit of the hose there. So as you know, P1 and P2 at the exit actually is both of them open. This is open to air. is not like it is open to air, so that's why it's open to atmosphere. So that's why P1 is equals to P2 equals to P80m. So it can be cancelled out. Also, the velocity at the gas tank, the surface gas tanks, as usual, if the cross-sectional area is so big, you can just take that velocity equal to 0. Okay, meanwhile, the velocity at the nozzle, at the hose, is quite noticeable, so you cannot just simply take it out, so it will remains there. And between these 2 points, Z2 is lower, so we just take Z2 as the reference 0. So you can just eliminate Z2. So this is the final expressions for the relationship between these. Okay, for the point 3 and point 2, where point 3 is at the higher part here, where it's above the HGL. Okay, so we do the same things again. Okay, we look at P2 and P3. So we don't know the pressure at 3. We don't know. So but we know the pressure at 2, where it is equals to atmospheric pressure. So P2 here is equals to P80m. And the V2 here and V3 here, they are the same. The velocity at 3 and the velocity at 2, they are the same. Given that the dimension, the cross sectional area of the hose is constant, so V2 equals to V3, you can just cancel them out. Okay, you can just take Z2 as the reference point 0 because it is lower to make it easier. So this is 0. So at the end you get the equations where atmospheric pressure equals to P3 over rho G plus Z3. So by this means that P3 is lower than atmospheric pressure. So this actually tells you that P3 here, since it is lower than atmospheric pressure, that means that it is vacuum. Okay, if you remember, so when you have an absolute and you have an atmospheric pressure, so if your absolute pressure is higher than atmospheric pressure, the difference is P gauge. But if your absolute pressure is lower than atmospheric pressure, this is P vacuum. So P3 here is vacuum because it is lower than atmospheric pressure. Okay, and this example velocity measurements by pipette tube. We have already discussed this before. Where point 2 here, this tube, it measures both the static and dynamic. Meanwhile, the one at point 1 here, it is only measures the static pressure. So actually, for this calculation, this P2 is the stagnation pressure, and it is equals to the static pressure plus the dynamic pressure at 1. So yeah, by just rearranging this, we can find the velocity along this pipe or V1. Okay, so by just finding the difference between the pressure, the stagnation pressure and the static pressure, and then we can find V1.